Okay, so in the last portion, I am going to discuss a useful application of the Jordan decomposition, something called the Cayley-Hamilton theorem. Okay, so I'll describe the theorem first, and then we'll look at how we'll go about proving it using the Jordan decomposition theorem. So we all know what the characteristic polynomial of a matrix is, right? So we have det of mu I minus a. Okay, that's the characteristic polynomial of a. Let's denote it by chi of mu. For the purpose of this lecture at least, so denote it as chi of mu. Okay, this is the characteristic polynomial. So what I am going to do is, so here for a matrix something like this, 1, 1, 1, 0, the characteristic polynomial is mu minus 1 whole square or mu square minus 2 mu plus 1. Okay. What I'll do is, in the characteristic polynomial, I will replace the variable with the matrix A. Okay. Replace the variable with A, the matrix A, and constant terms with identity. Okay. Meaning that here, for example, I'll replace the variable, mu is the variable, correct? For the polynomial, I'll replace it with a. So I'll write a square minus 2a plus 1, I'll replace 1 with identity. Okay? 1 times identity. Okay? Or you could have done it here also. We have mu minus 1 whole square. You can write it as a minus I whole square. That is also fine. Okay? Similarly, if the characteristic polynomial happens to be like mu cube minus 2 mu square plus 5 for some matrix, you will write it as, you will write the corresponding, the construction as a minus 2a square plus 5 I. Okay, it's constant here, 5 times 1 will be written as identity, so it is 5i. Okay, so this we are going to call chi a. Okay, so chi a is obtained by replacing the variable with the matrix, right, and constants with identity. The algebra will go through as usual, right? It's the usual thing, right? You could do this either in this form of the polynomial or even in the root form. So if you have mu minus 10 multiplied with mu minus 15 as the characteristic polynomial, the corresponding chi a will be equal to a minus 10i multiplied with a minus 15i. Okay. Okay. So why am I doing this? The Cayley-Hamilton theorem says that for any matrix A, if you find its characteristic polynomial chi and do this substitution, meaning instead of the variable you put in a and instead of constants you put in I, in the same polynomial that you obtain from the matrix, you will get 0. Okay, so that's the Cayley-Hamilton theorem. For example, if this were your matrix A, okay, if this were your matrix A, you know this is the characteristic polynomial. The Cayley-Hamilton theorem says that this quantity here has to be 0. A square minus 2a plus I has to be 0. Okay. So that's quite interesting, right? Because it's not very obvious. If somebody just gives you this matrix and asks you to say why this is 0, well, you'll probably just compute the whole thing and show that it is 0, right? But it's sort of immediate from Cayley-Hamilton theorem, right? So Cayley-Hamilton theorem has many applications, mostly having to do with powers of matrices, right? For example, here you can argue that a square is just 2a minus I. Right, so I don't have to compute a square. So if this is my matrix, right, if I know for some reason I know the characteristic polynomial of the matrix, then it's very easy for me to find matrix powers, right? So normally a square, computing a square will be order n square, right, order n cube, sorry, because you have to multiply, you know, all the terms will be order n cube, but it may not be order n cube because you can do it much faster. Okay, of course, I'm assuming I know the characteristic polynomial. Knowing the characteristic polynomial itself, it may be computationally expensive, but maybe in some scenarios you know the characteristic polynomial, right? Then finding powers becomes much easier by the Cayley-Hamilton theorem, right? So, for example, if I have to find a cube here, well, what will I do, right? I'll write a cube as, you know, a square times a, and a square itself will be 2a minus I, right, times a, I'll get 2a square minus a, right? But then a square again can be written in terms of identity, so a square is 2a minus I minus a, right? 2a minus I minus a, so you will get something like 4a minus a, that is 3a minus 2i, that will be your a cube. So in general, any power of a to the n can be written as some factor, which will be easy to determine in order n steps. Some factor times a minus some factor times I. Okay, so it gives you some advantage in terms of finding powers of a matrix. Okay, so that's the Cayley-Hamilton theorem. I hope the statement is clear. What we will do is we'll prove it using the Jordan decomposition. Now, interestingly, Cayley-Hamilton theorem applies for any square matrix A. Doesn't have to be symmetric, right? For symmetric, this is easy to prove. So let's do that first, right? What if A is symmetric? And I'm going to prove it using the spectral decomposition theorem as expected, right? So suppose A equal to VdV transpose, right? Suppose the eigenvalues of A are lambda 1, lambda 2 up to lambda n. Okay, so we know what is the characteristic polynomial, right? So it's got to be mu minus lambda 1 multiplied with mu minus lambda 2, so on, mu minus lambda n. That has to be the characteristic polynomial of the matrix, right? So what is chi A, right? So chi A is going to be, well, I have to replace the variable mu with A, right? So it could be A minus lambda 1i multiplied with A minus lambda 2i multiplied with A minus lambda ni. That's what I will get. So how do I claim that this quantity is 0? Okay, that's what I have to prove, right? To prove the Cayley-Hamilton theorem, or to prove this is 0. What I'll do is I'll plug in this expression. I'll plug in this expression over here into this. Okay, and I'll write I as v times v transpose. It's a standard trick that you might have used before. VdV transpose minus lambda 1 VV transpose. This is how I'll write it, right? VdV transpose minus lambda 2 VV transpose, and so on. Okay, now you can take VV transpose common outside, and what you will get is this d minus lambda 1i d minus lambda 2i, so on, d minus lambda ni times v transpose. This is what you will get. Okay, so recall what D is. D is a diagonal matrix, right? That looks like this: lambda 1, lambda 2, something like this, right? It's a 2 cross 2 example. Then you just have lambda 1, lambda 2 minus lambda 1 I. That is just going to be lambda 1, 0, 0, lambda 1. Okay, this is going to be the first term here, V, and then D is going to be like lambda 1, lambda 2 on the diagonal. I'm just taking a 2 cross 2 example to illustrate my point, right? And this is going to be lambda 2, lambda 2. Okay, this is going to be a V transpose outside here. Okay. Okay, now let's look at this matrix, right? So what will happen here in subtracting two diagonal matrices? We'll get a diagonal matrix. Well, here lambda 1 will cancel to give you 0 on the diagonal, right? And here you will get lambda 2 minus lambda 1, something that's possibly non-zero. Okay. And again here, if you do the same thing, you will get lambda 1 minus lambda 2 here, but on this diagonal you will get 0. Okay, and this V and V transpose outside. So what happens when you multiply these two matrices, diagonal matrices, is that in these two diagonal matrices, this diagonal matrix is 0 in the first position, whereas this diagonal matrix is 0 in this position. When you multiply them, you will get 0 overall. Okay, you will get 0 overall. You will get a 0 matrix, and hence this product is going to be 0. Okay, so that's the main idea behind the Cayley-Hamilton theorem. When you construct all these terms, right, you will get n diagonal matrices, but each of these matrices will be 0 in a different position. This will be 0 in the first diagonal position, this will be 0 in the second diagonal position, and this will be 0 in the nth diagonal position. You multiply all of them, you are going to get 0 overall. Okay, that's what Cayley-Hamilton theorem does for symmetric matrices, right? Generally, this is the trend. If something is true for symmetric matrices, to try to see if it is true for non-symmetric matrices, we'll try to apply the Jordan. Okay, right. So let's try to do the same thing for Jordan form. So you have A equal to Pj P inverse now. Okay, for A is non-symmetric, and let's say for the same reason, so your eigenvalues are, let's say, mu minus lambda 1 to the n1, mu minus lambda 2 to the n2, so on, mu minus lambda n to the n, lambda k to the nk, sorry. Okay, so let's say these are your eigenvalues. So when you compute chi A, you are going to get pretty much the same thing as before. So I'll just write down the final answer. Okay, it's going to be P times j minus lambda 1i whole to the n1, j minus lambda 2i whole to the n2, so on, j minus lambda ki whole to the nk times P inverse. Doing exactly the same thing you did for symmetric matrices, this is what you would get. Okay. Now let us try to look at each of these terms. So we will see a very similar thing will happen. Okay. Okay. So what is J? J is block diagonal. It's not diagonal like before, but it's block diagonal, and the blocks are the Jordan blocks. So this is going to be Jn1 lambda 1, Jn2 lambda 2, and Jnk lambda k. Okay. These are going to be the blocks. Okay. Okay, so now when you take them to the power of n1, right? So when you subtract like this, minus lambda 1i, so lambda 1i gets subtracted from everything. Okay, effectively lambda 1 gets subtracted from everything, and then you are taking to the power of n1. Okay, so this block is going to look like the following. This block is going to look like Jn1 lambda 1 minus lambda 1i whole to the n1. Okay, Jn2 lambda 2 minus lambda 1i whole to the n2. Okay, and similarly go on, Jnk lambda k minus lambda 1i whole to the power of nk. Okay. Okay, that's what this is going to look like. I skipped some diagonal entries here in between. This is what it's going to look like. Okay. Now what you see here is that this first diagonal block, this block is a Jordan block subtracted by lambda 1i, the same lambda 1 that is present in the diagonal of this Jordan block, taken to the power of the same order, n1 order. Okay, we discussed earlier that this quantity is 0. Okay, because this vector has all, this matrix has all the vectors e1, e2 to en1 in its null space. Okay, so this matrix is going to be the 0 matrix. Okay, these matrices could be something non-zero. In fact, these matrices will all be invertible matrices. Okay, if lambda 1 is different from lambda 2, this matrix will be invertible. Similarly, if lambda 1 is different from lambda k, this matrix will be invertible. All this will be invertible, this matrix will be 0. Okay, fine. This is the first term here. When you do the second term, you will see that the second block, okay, in this block diagonal matrix, the second block is going to be 0. And all the other blocks are potentially non-invertible. Okay. Similarly, when you take the last one, you will see that the last block will be 0. So basically here you have block diagonal matrices where in each of these terms a different block is 0. Okay, so here the first block is 0, here the second block is 0, third block is 0. When you multiply all of them, the blocks will multiply. You will get 0 throughout. Okay, so when you multiply this whole thing, you will just get 0 throughout. This is going to be a 0 matrix. Okay, and then P and P inverse here are incidental. 0 multiplied with anything will just give you 0. Okay, so that is the proof of the Cayley-Hamilton theorem. It tells you that no matter what the matrix is, whether symmetric or not, when you apply chi of A, you will get 0. Okay, fine. So this will finish our discussion on Jordan form. Cayley-Hamilton theorem is also useful to prove many other results. But we'll stop here as far as the discussion on Jordan forms is concerned.